So we've come a very long way in from looking at what uh, supervised learning techniques were. We looked at unsupervised learning technique where the model was actually trying to understand the patterns in the data on its own without the need of a labeled data. Now we are moving or inching closer to deep learning by looking at what is called reinforcement learning. This is actually a technique where it is not just identifying the patterns in data, which means we might not have that data in the first sense, but this is a machine learning technique that trains software to make decisions to achieve the most optimal results by mimicking the trial and error learning process that humans use to achieve their goals. A good example I always use, and I think I wrote it somewhere if I'm not wrong, is the baby. When the baby is growing, uh, when you are a baby, there are some things that you are always being done for. For example, when you start crawling, the baby always becomes touchy, want to touch everything around. Then a good mother will always leave a lamp, a lightened lamp, so that the baby touches this lamp, and next time when he crawls, the lamp had burned him or her before, so he will not touch it again. So that's the trial and error learning process that we are talking about. As he grows, let's say he's now 9 years old, the baby is being taught to perform house chores. But in this way, like in our home, our mother used to award anybody who would wash dishes or collect firewood or perform well in school. So the baby grows up by knowing that this is a good thing that is always rewarded and this is a bad thing that is always punished. That is exactly how reinforcement learning works. So reinforcement learning is a machine learning technique that trains software to make decisions to achieve the most optimal results by mimicking the trial and error learning process that humans use to achieve their goals. Software actions that work towards your goals are reinforced, while actions that detract you from the goals are ignored. And in fact, sometimes punished. So, like we said, like the use case of the baby, that's exactly how it works. So, when the baby touches the lamp, is actually being punished. When you are 9 years old, when you are told to wash dishes by your mother when she was going to the market, coming back, she found out you've not done it. You are being caned and even denied food. But when you do it, you are being rewarded with some two mandazis or some pair of slipper or flip flops. So that's exactly how reinforcement learning works. So that next time, automatically without you being told, hata mtakuwa mnang'ang'ania kuosha hizi vyombo. So reinforcement learning algorithms use a reward and punishment paradigm as they process data. They learn from the feedback of each action and self-discover the best processing path. Yes. Ah, Jesus, sorry. I'm not. The recording is being done. Thank you for that. Hope you can see my screen now. So, and self-discover mm, the best processing paths to achieve final outcomes. The algorithms are also capable of delayed gratification. The best overall strategy may require short-term sacrifices. So the best approach they discover may include some punishments or backtracking along the way. Backtracking is basically to redo. Reinforcement learning is a powerful method to help artificial intelligence systems achieve optimal outcomes in unseen environments. So, with that short or brief introduction to reinforcement learning, I hope you've now gotten the picture or the concept behind it. And how does this reinforcement learning thing works? The learning process of reinforcement learning algorithm is similar to animal and human reinforcement learning in the field of behavioral psychology. For instance, a child may discover that they receive parental praise when they help a sibling or clean, but receive negative reactions when they throw toys or yell. Soon, the child learns which combination of activities results in the end reward. An RL algorithm mimics a similar learning process where it tries different activities to learn the associated negative and positive values to achieve the end reward outcome. Reinforcement learning does not require data. Instead, it learns from the environment and reward system to make better decisions. So basically just reinforcing what I talked about in the previous slide. Some concepts that we are going to find in in this learning journey include the agent, the environment, the action, the state, the reward, and the cumulative reward. Later, I'm going to before we start looking at the agent, I'm going to use the baby or the child, the boy, 99-year-old boy who is still under direct parental care. So this boy is the agent in this case. The environment is the house or the homestead. The action is what this boy is going to do, and the state is the particular time or the particular thing the particular time that an action is taking place. The reward is what is given for a particular action, while the cumulative reward is the total reward that you've gotten from many actions. So the agent is the one we are always going to build first. Then we give it the environment, then the action it does, then the state, then the reward for a particular action, then the cumulative reward for the entire learning process. So when we look at the agent, this is the machine learning algorithm or the autonomous machine learning software system developed to solve a problem and thereafter provide a solution. A good example is when you look at the self-driving car. The app that drives that car or the system that drives that car is what is called an agent. Yes, it not necessarily it does not necessarily that's why you mention it's an autonomous machine learning software system. It does not have to be a tangible thing. Even the system built, the algorithm built can be the agent. Self-driving car, the algorithm that is built to drive that car is what is called the agent. That's why you cannot see it and there is no driver. The environment is the adaptive problem space with attributes such as variables, boundary values, rules, and valid actions. So the environment is where this car, for example, a Nairobi city where this or New York City where the self-driving car will cruise through is the environment. So the variables can be roads, street lights, police officers. You see these things like that. And the rules are that you must keep left, keep right if you are in US. And valid actions. The valid actions are where you stop when there is a zebra crossing. So this is what is called environment. So the environment is the adaptive problem space. And what is in the environment are what are called attributes, which include variables, boundary values, rules, and valid actions. Yes, yeah, sure. When it is able to stop when it detects a zebra crossing or street light, then that is a valid action, and it is rewarded. So the reaction is the step that the agent takes to navigate the environment. So you can imagine a self-driving car when it was being developed and tested. Actually, what is done, they do what is called simulation. An aerial picture of New York City will be taken, then a very large field will be built. Like this one is something that a very big company is the only one that can do. So you simulate New York or Nairobi City the way it is. Then after simulating Nairobi City, you now start building the car in that simulated city, which is basically a very big field with which has been built exactly as Nairobi should look like. Not exactly, not necessarily exactly, but near exactly. So at the end of the day, when it's taken to Nairobi, it actually gets the feel. And you can now use Nairobi to train it for other cities also, because what is in Nairobi may probably be found in other cities. Street lights, police officers, zebra crossing, roundabouts, things like that. So the action is gonna take in an environment or in a space is basically the step is basically what is called an action. And these steps include for a self-driving car, taking a roundabout, stopping when it detects a zebra crossing and there is street lights, and it's stopping when it detects a police officer. So things like that. Now the state can now be given two circumstances. Number one, the environment at a given point in time. For example, when it stops, that's a state. The state focuses on the traditional understanding of the real reinforcement learning framework, where the state represents the environment's current configuration or situation. In reinforcement learning terminology, the state is a snapshot of the environment's observable characteristics at a specific point in time. The state is a snapshot of the environment's observable characteristics at a specific point in time. For example, the red light. The red lights signify that all cars should stop, and that's a state. So when the car stops, that's a state. No, no, when the car stops, that's an action. While the environment says that the car should stop, that's a state. So the agent's decision-making process is based on its perception of the environment, which is encapsulated by the state. Yeah. It again drives. If you kwa roundabout, it takes about turn. That's a state, the state of the environment when it takes a roundabout. But also, the state can also be the user. This statement appears to emphasize a different application domain where the concept of state is extended beyond the traditional reinforcement learning framework. In this context, state may be referred to the user's characteristics, preferences, behavior, or any other relevant information that influences the decision-making process. In this perspective, suggests that the state presents incorporates aspects of the user's context. For example, let me use an example. The route that it was supposed to take, it has predicted that there is traffic. So it navigates into a different corner altogether. That's also a state. So, like when you want to beat traffic, instead of using the normal route, the Waiyaki way, you decide to use a different route altogether. Self-driving car have also been built to do that, and that's a state. The reward. This is the positive, negative, or zero value. In other words, the reward or punishment for taking an action. The zero value, nothing. The state is still as zero. The positive reward, umefanya poa. The negative reward, umepewa punishment. So for it is rewarded for taking an action. Then you also have the cumulative reward, which is the sum of all rewards or the end value. At the end of you see the reward is given at each and every state and action. So when you stop when there is the zebra crossing and the red street lights, you get a reward. But when you pass, you get a punishment. Again, when you stop when the police officer stops you, that's a reward. So that's the reward itself is given at a specific at a specific state or action. But the cumulative reward is actually the average of all these rewards. Yep. No, 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 no. I said the average. So we sum up both the zeros, negatives, and positives, and then we divide by the number of states or the number of actions you had taken before. Yeah. So at the end of the day, if you had so much punishments than positive rewards, then what do you expect? Punishment. So we take you back to the lab and develop you afresh. And by the way, this is an iterative process, and that's why the project takes uh, decades. Some of them have been abandoned even before they are done. Like Google had to abandon theirs and buy a company called Waymo. Amazon had to, yes, Amazon had to abandon theirs in entirety. Like for them, they just abandoned it for good. They did not want to continue. So the Waymo self-driving car, not formerly known as Google self-driving car. So this self-driving car was purchased by Google from a company from a company that had developed it. So this it happens. So it happens, and they drop it. They drop it altogether and continue with another thing that works for them. Amazon had to drop theirs. Amazon had to drop theirs. It didn't even live to see 5 years. Google dropped theirs and purchased this new one. So, so that's it. So you can watch the video. There you go. So that thing it stops. Did you see that? Ah, yeah. When you order it, when it reaches your position where you should board, it stops. So this is all reinforcement learning. Again, this reinforcement learning, it can also be integrated with the deep learning. But more of this will be in the AI engineering course. If we were to develop this, like I said, it's going to actually take decades for you to reach here. And also, the reason why limited resources prevent us from developing this, it fits a lot into the computer memory. Or you think people complaining that their computers are busted is always a fallacy? It's a reality. Up to that point, are we together? So basics of reinforcement learning algorithm. What makes up the reinforcement learning algorithm? What you are going to uh, come across. Number one is what we call the Markov decision process. We also have the value functions, the policies, the exploration and exploitation, which is my best one actually because it's always easy to. So the Markov decision process is MDPs. In MDPs, the outcomes depend on the current state and the chosen action. I mean, that's self-explanatory. So the outcome or the reward you are going to get will depend on the current state and the action you take for that state or in that state. So if the current state is a roundabout and you are supposed to take a roundabout, then then the outcome should the reward you are going to get should depend on what you are going to do. So by assuming the Markov property, which said that the future is independent of the past given the present state, Markov property states that the future is independent of the past, meaning at state one, and we're going to see this in practical. What you take at state two is totally independent of state one, meaning now that the rewards at state two might be different from state one. Which says that if there are two roundabouts in one highway, then probably when you did not take a good turn in the first roundabout, but but it doesn't mean that you will not take a good turn in the second roundabout. So these two things are independent. The future is independent of the past given the present state. So the present state in this case is taking the roundabout. So the roundabout is in set one and the roundabout is in set two. So when the car moves, instead of taking a roundabout vizuri, inaenda direct inaingia kwa roundabout. So inagonga the pavement, inarudi nyuma, inago, oh, this is a roundabout, then it takes the roundabout. In the second one, the car, don't be surprised when the car takes the roundabout perfectly because these two things are independent. And remember, we said it keeps on learning as it navigates the environment. So MDPs enable agents to make sequential decisions efficiently. Sequential meaning in a sequence, this after this as you move along. Then at every step, the agent takes a new action that results in a new environment state. I have explained that. Then similarly, the current state is attributed to the sequence of previous actions. So the current state attributed meaning the future, even though it's not dependent on the past, it, the future learns from the past. Yeah, just like human beings say, I've learned my lesson. So that's, that's exactly what the cars do. They learn their lessons from the past, but the states are independent, meaning if they were to be dependent, then probably the cars would have always been very much efficient. So these are independent. What it's going to do in the first state is different from what it will do in the second state, and so on. So Markov decision process actually is a sequential process that states that the future and the past, given the present states, are independent. Kizungu kubwa. Then we also have the value functions. The value functions estimate the expected return from the word value actually. The expected return or utility of being in a particular state or taking a specific action. They quantify the desirability of different states or actions based on the cumulative rewards an agent can expect to receive. By optimizing value functions, agent can make informed decisions that maximize long-term rewards. In short, this is just another name for reward. So, because rewards quantify the desirability of different states, what is this particular state going to give us as a reward? So if we can quantify that, then that's basically what is called the value functions. So when we can actually use this with deep learning functions like neural networks, then it's going to be used to predict the rewards. So that's when the value functions come. You are able to predict the rewards. So what did you say about Markov decision process? It's a sequential step that tends to compare the present and the future, which are future states which are independent. The value functions tend to quantify basically a reward, another name for reward, and also we have policies. I mean, these are just laws. So these policies define the strategies that agents use to select actions in different states. They map states to actions and guide the decision-making process. So remember, we said that each and every company has their own policies. So this is exactly what the policies we are talking about in the companies is actually borrowed and now is being used in reinforcement learning. So they are the ones that are being used to guide the decision-making process. For example, I love using this example. If this is a road, let me bring up the paint. If this is a road, in Kenya huwa tunachorewa, acha niweke na yellow. Mhm. Policy number one is that you must keep left. That's a policy in Kenya. Policy number two is that you should not drive while meandering at unaenda hivi. It should be a straight line. Policy number three is that when you want to overtake, keep left unless overtaking. You must overtake with the right now. Policy number four is that you should not drive off the road. Meaning, or even drive hapa, overlap. You should not overlap to achieve pedestrian supper. These are the policies we are talking about. And you should not see this one here katikati. I don't know how it's called. Inaitwanga aje? You must know because wewe si civil engineer, wewe ni architect. An architect. Yeah, but now you, you should not also go to the other lane, otherwise you'll cause accidents. That's exactly what is called a policy. Policies can be deterministic, where each state maps to a single action, or stochastic, where each state has a probability distribution over possible actions. So deterministic is very much direct. A state maps to a single action. So which means that given a state, there is an action is going to take. But stochastic, which is always the one that is recommended, where each state has a probability distribution over possible actions. So when you have a stochastic process, it basically means that given a state, the car can take so many uh, different actions. For example, kuna roundabout hapa, so barabara imetengenezwa ikuje hivi. So when the car comes here, maybe it can go roundabout ndio iende tena. Nice. So if the car comes here, let's say maybe this road was leading to somewhere like that, na ilikuwa inataka kuchukua hii route hapa. So when it takes that, when there is only that one possible action, then that is deterministic. But what if the road was this way, such that there is another road here, which take you back, but will lead you to this other. So which means that the car can come and take this road. Ikiona hapa kuna traffic, it can come and take this road here, or it also add the probability of taking this. So when we have probability distributions, like it could go with this route or go this route, or even reverse back, then this is what it's called stochastic. Tuko pamoja hadi hapo sasa? The choice of policy greatly impacts the agent's behavior and the effectiveness of reinforcement learning algorithms. The keyword is greatly. Those policies must be implemented. The last one is exploration versus exploitation. The car is a tourist, it explores, then once it gets something that can help in maximizing rewards, it exploits. One of the fundamental challenges of reinforcement learning is the exploration exploitation trade-off. Exploration involves trying out new actions to gather information about the environment and discover potentially better strategies. So to exploit, basically, you're trying new actions and see if it's going to work. While exploitation, on the other hand, use the knowledge gained so far to maximize immediate rewards. So exploration, you try out new actions. When this new action works, you leverage them. When you leverage them, that's what is called exploitation. Just from the English word to exploit. Striking the right balance between exploration and exploitation is crucial for efficient learning and optimal decision making. So the agent must also choose between further environment exploration to learn new state action rewards or select non-high reward actions from a given state through exploration exploitation trade-off. Uh, the agent must also choose between further environment exploration, meaning it can continue performing other actions to see if they are going to work, or it may select a high reward action. For example, it might not continue exploring, but it can exploit. Sinajua it had explored and kept rewards of different actions, so it might use one of the highest rewards. So this is called exploration exploitation trade-off. So we talked about four basics of reinforcement learning: the MDP, Markov decision process, the value function, the policies, are now the exploration versus exploitation trade-off. Mm. No, 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 no. Hapa kuna parameter, by the way. These are non-parametric tests. What is happening here? We are just going to initiate a list of rewards, an empty list. So as the car performs an action, we append a reward there. When it flops, we append a punishment or else zero. Then after that, by the way, you will see the codes that will be generated here. They're always very, very senior engineers code. Because for you to be, you have to be a specialist. That's honesty. I have to be honest with that. And for you are conversant with Google employing for senior software engineers 10 to 15 years of experience. Yeah, so they are the ones who do all this. So what happens is that after after pending all these rewards during exploration, then if you do not want to continue with the exploration, which you are going to tell it that if there is a certain number of or k number of explorations, you can now exploit, which you are also going to define. Exploitation equals to, you can now choose from that one. So for example, exploitation equals to exploration reward in the list which we are the exploration list, if else that else zero. So it's basically in one word you've written a for loop or and also something like that, and if statement. Jamani, tuko pamoja, are we together? I know you are really enjoying this unit. I also enjoy it anyway. Then types of reinforcement learning algorithms. So actually, to implement it, I always use one. I use DynaQ or Markov something. You're going to see it. And we always build a game. The game we build is a tic-tac-toe game. So the game plays with you, but it uses the model which you built. This game, this game adapts as you continue playing with it because it gets rewards. Then at the end of the day, you cannot beat this game. While starting out, it's okay. It's okay. You can beat it the way you want. But as now time progresses, it rambas you kiasi. So types of reinforcement learning algorithms. Before we dive into the various types of RL algorithms, let's first understand two main groups within this model. There is what is called model-free reinforcement learning and model-based reinforcement learning. And there is also another model that combines the two. Model is both model-free and model-based. We are going to see how. So in model-free RL, model-free RL is best to use when the environment is large, complex, and not easily describable. The self-driving car uses model-free. But again, since we are simulating, that's a model-based. The environment is small, can be simulated, model-based. So at the end of the day, you are going to realize that the best model to use is the one that leverages both model-free and model-based. But I'm saying for it to be model free, the environment is large, complex, and not easily describable. It is also ideal when the environment is unknown and changing. Today, a city can have, for example, the former president built us a very nice expressway. You can imagine the car that had been trained, as a driving car that has been trained that there is only Uhuru Highway. Then all of a sudden there is an expressway. So the environment is unknown and it keeps on changing. So, and environment-based testing does not come with significant downsides. So the agent does not build an internal model of the environment and its dynamic, and that's why it is called model-free. The agent does not build an internal model of the environment and its dynamics. It will learn. It will learn from the changing environment. But if you build an internal model, meaning you are the supply that it will never change. So you will ask, then where can we use, because you've seen where we can use model free self-driving cars, then where can we use model based? Model based is mostly used to develop robots working in a company, where they know where to pick things and where to take them and how to move. That is basically how you can leverage on model based. And you are going to see now in model free, the agent, the reason why it is model free is because the agent has no known environment dynamics built in its system. It will learn from the environment that it will be taken to. And instead, it uses a trial and error approach within the environment. And I have explained that by saying it will learn. It scores and not state action pairs and the sequences of state action pairs to develop a policy. Sequences meaning state action pairs, it basically means that state action in different states, what are the actions and what are the rewards in the next state. That's the sequence it takes, and that's model free. What a real world example is the self-driving car that needs to navigate city traffic, roads, traffic patterns, pedestrian behaviors, kwanza Kenya, and countless other factors can make an environment highly dynamic and complex. AI teams train the vehicle in a simulated environment in the initial stages. The vehicle takes action based on its current state and receives rewards or penalties. Over time, by driving millions of miles in different virtual scenarios, the vehicle learns which actions are best for each state without explicitly modeling the entire traffic dynamics. When introduced in the real world, the vehicle uses the learned policy but continues to refine it with the new data. Woohoo! See how powerful AI is. Then most commonly used model-free reinforcement learning algorithms, deep Q networks or uh, DQN. We have Q learning. You're going to see why it is called Q learning. We have state action reward state action, which means that SARSA means state action reward. Based on the reward, you also take it back to the state, and so it's a sequence that we're talking about, the MDP sequence that we're talking about. Then we also have the policy gradients, the proximal policy gradients, and we also have the Monte Carlo methods. Q learning. Q learning is a model-free, value-based off-policy algorithm that will find the best series of actions based on the agent's current state. The Q stands for quality. That's why it's called Q learning, which represents how valuable the action is in maximizing the future rewards. The reason why it's called Q learning is because it emphasizes more on optimizing the rewards for high quality. So Q stands for quality. The rewards, I told you that reinforcement learning thrives on getting the best rewards. So if we can find a model that actually uh, optimizes these rewards, then that is the best model. Q learning is one of them. So Q learning estimates the value of set action pairs and iteratively updates the Q values based on the observed rewards. So by learning an optimal policy directly from experience, Q learning enables agents to make intelligent decisions. So the terms used in Q learning include model free. I had explained model free. The algorithm learn the consequences of the actions through the experience without transition and reward function, while value based. This method trains the value function to learn which set is more valuable and take action. So you remember value functions? We choose from the best value reward. Then off policy, the algorithm evaluates and updates a policy that differs from the policy used to take an action. Off policy meaning that if the if there's a policy that we used to take an action, but it didn't work for us, we actually assume that policy. We use a different one altogether. It doesn't mean off policy. Students used to interpret it as if that there is no policy. There must be a policy in RL. Except that off policy, it means that if the policy is not giving us what we want, we use a different policy. The state is the current position of an agent in an environment. The action is a step taken, the reward, and now the last one is the episodes. The end of the stage where agents can't take new action and happens when the agent has achieved a goal or failed. So, so episode 1, tukimaliza episode 1 inamaanisha tumemaliza, tunapata cumulative rewards. Aya, some mathematics. Ooh. S stands for state, small letter A stands for action. So Q, ST plus 1 given action. Expected optimal Q value of doing the action in a particular state. The T plus 1 stands for, like it is a sequence. The use of QSTAT. This is the current estimation of QST plus 1A. The Q table. The agent maintains the Q table of sets of states and actions. The Q table is basically a table that represents a set of actions and like states action pairs. Then the temporal differences TD. This is not traditional dance. It is temporal differences. It's used to estimate the expected value of Q. You see, in such like mathematical things, we cannot always find Q ST plus 1 given A. So we always estimate. So when we estimate it, we use what is called the temporal differences. And we do this by using the current state and action and previous state and action. So the previous state and action is QST AT. The current one is QST AT. The previous one is QST minus 1, AT minus 1. The next one is QST plus 1, AT plus 1. The next one is QST plus 2 Ivo. Yep. How Q learning works? Wacha ni kidogo hapo nitarudi. That's Q learning. Another one is called deep Q networks or DynaQ. This no, is it the one? I think it's no. DNQ is the one called DynaQ. So deep Q networks combine reinforcement learning with deep neural networks. So DQNs use the power of deep learning architectures to approximate the Q values of large state action spaces. I think I had actually hinted on something like neural networks sometimes back. Yeah. So when you can combine Q learning now with Q learning now with neural networks, then that is called deep Q networks. So by employing neural networks as function approximators, DQNs can handle complex environments and learn high-dimensional representations. I cannot talk about it when we've not talked about Q networks, but I cannot tell you that we are going to look at it. This is when we are done with it. But after looking at after looking at neural networks, you will now see how neural networks can be used with Q learning, which we are going to look at in depth. The use of policy gradients. The policy gradient methods directly optimize the policy by estimating the gradients of the expected rewards with respect to the policy parameters. So here, it optimizes the policy by estimating the gradients of the expected rewards. And what is the gradient? What gradient are we talking about? The gradient, the expected reward is actually the rewards in the current state given the rewards in the previous state divided by. When you talk about gradient of a line, of a set line, inakwanga see where m, so the m here is the gradient, that's a function. M in this case is the gradient. So what do we say? It's change in y all over something like that. So it's actually the change in rewards. The change in rewards all over given the policy. So this is the policy gradient. By iteratively updating the policy in the direction of higher rewards, we update it in the direction of higher rewards. This method can learn complex and continuous action policies. They have been successful in applications like robotic control and natural language processing. Again, that one we are not going to touch on. Otherwise, if we were to touch on all these, then it means we'll need 2 years. It will be a diploma in machine learning. We also have even 3 years, should be three. Proximal Policy Optimization PPO. Diploma in MLOps Engineering, that's 3 good years. So PPO is an optimization algorithm that maintains a balance between stability and sample efficiency. How? PPO uses a surrogate objective function to update the policy parameters and ensure small policy updates to maintain stability. What we are going to do here, actually the explanation comes from the name, policy optimization. We are optimizing the policy to actually ensure that we get higher rewards. So the policy is the one we are updating, not if the environment, but the policies. For example, if we go back here, look at this, the pedestrian lane. Kama ni kubwa, tunaweza ifinya sana so that we do away with the pedestrians and give the car a wide allowance where it can now drive. So you see that one will increase the reward. So that is what is called proximal policy optimization. So it's the policy that we are updating. The set action reward set action pairs. This one is self-explanatory. It's basically for each and every set and action, we give a reward and update sequentially as the algorithm performs its task in an environment. So Sarsara is another model-free reinforcement learning algorithm that is similar to Q-learning but updates the Q values based on the current action and next action. Q-learning, we say it updates based on the best reward. That's why it's called for quality purposes. But this one, based on current action and the next action. That's why the state action reward. Then we move to the another state action reward, so on and so forth until we reach the episode. So it is applicable in fields such as robotics and traffic systems. Monte Carlo method. Monte Carlo method estimates the value of states or set action pairs by averaging returns obtained from multiple episodes of interaction with the environment. Multiple episodes meaning we've now gotten multiple successes and failures. We started over again, it failed, and an episode is gone. We did it passed, an episode is gone. So at the end of the day, Monte Carlo method says, you know what, we should not just leave this one go. Let us average them. These methods are model free and particularly useful when exact transition probabilities are unknown, or when the environment is episodic. When the environment episode we said is the end of each and every trial. So when the environment can actually help us get episodes, then that's where we can use Monte Carlo, because we are going to average for each and every episode for all the episodes. For the environment to be episodic, there's a green explanation there. The agent interacts with the environment in a series of episodes, with each episode consisting of a sequence of steps leading to a terminal set. Remember, each episode is basically a Q-learning reinforcement technique on its own, meaning there were it might be a Sarsa or a Q-learning that was happening in an episode. So when we have like 20 Sarsas or 20 Q-learnings and average them, that's what brings up Monte Carlo. Now let's talk about model-based, then go back and finish on Q-learning. And the reason why I want model-based is because tomorrow when we are looking at a certain model that we are going to build under this, it is going to leverage both on model-based and model-free, especially the games. So for model-based, and I think the mind is also somehow very still. So what can we do? We can take a 10 minutes break and come back. Theory needs some break. So we come back at 10:40.